Hello. In this presentation, I will talk about three classic algorithms from dynamic programming. These algorithms are equivalent in the final solutions that you can get. And these are algorithms for estimating the value function of an MDP. So to start talking about these algorithms, we need to talk about policy evaluation. If you remember, a policy is a function. We call this policy policy pi, which is the function pi. And the policy function tells you what is the probability that given that you are in a state S, the action that will be executed will be action A. So it's a probability distribution over all pairs of states and actions of your MDP. So in terms of the policy evaluation, we say for a given policy pi, compute the state value function v pi. So given a policy pi, we need to estimate what are the values of each of the states of our MDP. So we need to estimate v. And here's the definition of value function for a policy pi. So for every state, you need to calculate what is the expected return that you will get if you start in that state, or if you are in state S and you keep selecting actions according to the policy pi. So this return we have defined it before as the sum from k equals 0 to infinity of the discounted rewards that you will get as you keep doing actions from state S, so from time step t. Remember also that this gamma is a value between 0 and 1. We also defined previously the Bellman equation for a value function and the policy pi, and the value for each of the states can be calculated with the calculation of the following probabilities. So here, remember, this is the expectation, this is the expected value. If we want to calculate this as a probability, then we need to consider the probability function pi, which is the policy function. We need to consider the probability distribution of the transition function. And we need to consider, of course, the reward function and the current value of our states. So basically the algorithms that we are going to study are algorithms that allow us to estimate this value function. They will be used for solving the Bellman equation. So the strategy is to iteratively approximate the value function. So we will initialize our function, we will have some v0, and we will apply our algorithm in one iteration to get the next version of the value function. So this is v1, and we will be doing or applying this algorithm until we reach the final policy, the final value function, sorry. Every time we move from one version to the other version of the value function, we say that we are doing a sweep. And a sweep means that you need to update the value for every one of the states in your MDP. So to go from the value function k to a value function k plus 1 in an MDP that, for example, suppose that your MDP has 20 states, you need to update the values of your 20 states, and once you have done that, you have generated the value function in the next iteration k plus 1. So a sweep consists of applying a backup operation to each state. A full policy evaluation backup consists then in applying this rule, which is the Bellman equation, to update the value for every state in your MDP. So I will show you with a small example how you can create pi, p, r, and v, so it will be easier to understand the algorithms. Okay, so here we have an example. Suppose that our MDP has only 3 states. From state 1 you can go to state 2. From state 2 you can go back to state 1 or to state 3. And from state 3 you can go to a state 2. So this is an MDP with 3 states, 1, 2, and 3. And I am considering here that we have available only 2 actions. The action going left, that will be called action 1, and action 2 will be going right. So we need to estimate the values of each of these states. We can construct a table like this one, where you have an entry for each of the states. We have 3 states, so we have 3 entries, and you can initialize the value function with zeros for every state. Depending on the algorithm that we will implement, we will be updating these values after each of the iterations. So if we want to apply full sweeps, that means that we will need to update these 3 values. Now we have some functions that we need to define. Here is the definition of the policy function, which is the pi function. Here is the definition of the transition function, or the p function, and here I have defined the reward function. So in the case of the policy, you need an entry for each pair of state and action. So since we have 3 states and 2 actions, 3 by 2, that's 6, so we will have 6 entries for each of the combinations of state and action. So here is state 1, action 1. We have state 1 and action 2, state 2, action 1, and so on. Now imagine that you are in state 1. In state 1 you can execute the action go left, and the result of that will be that you will remain in state 1 because there is no other state here. Okay, so that's the rule in this exercise, in this MDP. if you are in 1 and apply go left, you will stay in state 1. If you are in state 1 and you apply right, you will end up in state 2. Okay. In state 3, it's something similar. If you apply go right, so action 2, you will stay in state 3. If you apply go left, you will move to state 2. And in the case of 2, if you apply action go left, you will end up in state 1. If you apply action go right, you will go from 2 to 3. Now this policy, remember that this policy is the probability that if you are in some state S, the action selected to be executed is going to be action A. What we usually do in these algorithms that we are going to study, these 3 algorithms that we are going to study, is that we give the same probability to each of the available actions. So we have only 2 actions available. We give all these 2 actions the same probability, so that would be 0.5 and 0.5 from each of the states. So if you are here, you will have the same probability to select action go left and action go right, so that will be 0.5 and 0.5. Suppose that instead of having 2 actions, we had 4 actions, like going up, down, left or right. We need to give the same probability to all these 4 actions. So the probabilities then would be 0.25 to go up, 0.25 to go down, 0.25 to go left, and 0.25 to go right. Okay, so in this case we have only 2 actions, so the probability will be 0.5 from each of the states. Okay, so if you are in state 2, again you will have a probability of 0.5 to go left and 0.5 to go right. And the same happens with state 3. That's why you have here 0.5 in every entry. So that's the way you define the policy function. The transition function, as the name says, it tells you the transition probabilities. So if you are in state S and you execute action A, what is the probability that you will move to state S prime? So you need to create a table with all the possible combinations of S, A and S prime. S, of course, makes reference to all the possible states in your MDP, which are 3 states. Actions make reference to these 2 possible actions, and S prime makes reference also to every possible state in your MDP. So this is 3. So if you build the table completely, you will have 3 by 2 by 3 entries in this table. Okay, so in this case I have built only the first 18 entries. So here it is very important to understand how this table works. If you are in state 1 and you go left, the probability that you will stay in state 1 is 1. Okay, so if we are here and we go left, we stay in the same state. So that's for sure, that's going to happen for sure. So the probability of that occurring is 1. Now the next combination, if you are in state 1, if we are here and we say go right, the probability that we will stay in state 1 is 0. Okay, because if we are in state 1 and we execute go right, you will move to state 2. Okay. So in this MDP, there are only two possibilities that will have probability 1, and all of the other combinations will have probability 0 to occur. Like this would be the second possibility for that state. If we are in state 1 and we go right, we will move to state 2 with probability 1. Okay. All the other combinations are impossible. Like if you are in state 1 and you apply go right, it's impossible to move to state 3. So the probability is 0. Okay. If we consider state 2, okay, we have here, if we're in state 2 and we go left with probability 1, we will move to state 1. If we look at this entry, if you are in state 2 and you move right, you will move to state 3 with probability 1. All the other possible combinations are impossible, so the probability is 0. And the last block we have, if you are in state 3, you apply go left, the probability of moving to state 1 is 0. Okay, the next one is also 0. Then we can check the possible movement. So if you are in state 3, go left, you go to the state 2, that's probability 1. And if you are in state 3, you move right, you will remain in state 3. So okay, in this case I already built the whole table. I thought I needed more, so this is wrong. Here this table is complete. So the point is that these probabilities, as you see, in a very small MDP, you can generate very long tables. But in this case, this is complete. Okay, we have all the possible combinations of S, A, and S prime, and the same happens with the reward function. Okay, so this is wrong because this table is complete. Now the reward function is given by the programmer. Okay, in this case I am assuming that the goal state is going to be state 3, and I created the reward function in such a way that if the agent enters state 3, the agent gains a reward of 10. Okay, otherwise it gains always 0 points. Now there are some of these entries with reward 10 that are impossible to occur. Like in these two cases, I'm saying if the agent is in state 1 and moves into 3, it will gain 10 points. But we know from the dynamics of this MDP that from 1 it's impossible to get to state 3 directly. First you would need to go to state 2. So even though the reward says that it will get 10, it will get 10 if, for example, in this case, staying in state 1, applying action go left, somehow the agent ends up in state 3. But according to the current dynamic of this MDP, that's impossible. If at some point the dynamic changes and by applying this we allow the agent to go magically to state 3, then this would happen sometime, but this is impossible to happen at the current dynamics of the MDP. So here we have again the situation that we will have 10 points in state 3. This one here is the only possible according to our transition function. Okay, so if we are in state 2 go right, then we will move into 3 and then we will get 10 points. And in this other block here of the reward function, the only possibility is also the last entry, which is going from being in state 3, applying action 2, so going right, and you remain in state 3. That will be also again a reward of 10. So this means if the agent is in state 3, applies go right, since it will stay in state 3, will get again the reward. Now, if you are applying this, sometimes you will say, once you have entered the goal state, the episode terminates, so you stop running the algorithm. But this will depend on the way you want to implement this and the way the MDP works. So the idea of this exercise is to see each of the elements in the Bellman equation, what they mean, okay, and how you need to implement it in order to apply the algorithms that we're going to study.